Hello, Shweta, can you hear me? Hello, Shweta, can you hear me? Checking.
Yes.
Okay.
Hmm.
Right. Wait for a couple more minutes before we start. Right. Yeah. Okay, I think I'll start. Um, oh, second. So this week we'll be covering the content of week 3. So so this is the agenda for today. So we'll be covering some properties of Poisson and exponential distributions that we would need for various proofs. And yes, like and then like we'll also be covering the theory of continuous time Markov chains, and we'll solve some problems. Yeah. Right. Okay. Wait till 305 maybe, then we'll start. Okay, I'll start. So as you can see, this is the Poisson distribution it's a discrete time distribution as we know it. So this is the probability mass function of a Poisson distribution as we will be using it in the context of queuing theory. So, normally the mean is lambda, but instead of lambda, we have here lambda t because lambda is typically the rate of arrivals or departures or some quantity per unit time. So we multiply it by time to denote the average, let's say, number of arrivals in a time interval of t, right? So the probability that n, let's say we have a queue here, and lambda is the arrival rate. So lambda people per second, let's say. So the probability that there will be n people in the queue. So probability that there will be n arrivals in the queue, like in the interval of 0 to time period t will be this. So yeah, that is one important property. And so corresponding to this, it can be shown that the time interval t spent by a packet in the queue will be, for a Poisson distribution corresponding to this will be an exponential variable of with the parameter lambda. So yeah, this will be like, so that the time taken will vary as, let's say, something like minus lambda t. So this will be the time. This is the distribution of the time, obviously lambda greater than 0, of the time spent by like a, sorry, something like this, right? So this is the exponential distribution of the time spent by like a person in a queue, right? So okay, Tausif is back. So we do have a question. So let's say, let us draw a timeline, right? We have the time axis here, and we start at time t equal to 0. We have a time interval t1. Let's just draw a random time interval t1 to t3. So my question is, and then we want to check, we want to count the number of arrivals n from, let's say, 0 to t1, and we also want to count let's say all between all of these intervals, right? We also want to count n t1 to t2, and we also want to count n t2 to t3. We want to count that in this queue, how many people are arriving in the queue according to the Poisson distribution, how many people are arriving in the queue in these time intervals. My question is, are these quantities anyway dependent on each other? Are these quantities anyway dependent on each other? These three quantities. Number of arrivals between 0 to t1, t1 to t2, and t2 to t3. Is there any dependence? So the answer is no. That is the inherent property of the Poisson distribution, that there are independent. So this is the notion of independent increments. That disjoint time intervals like 0 to t1, t1 to t2, t2 to t3 are completely independent of each other. So there is no correlation or no dependence on one quantity on the other. So regarding that, we can kind of solve a very simple problem that excuse me. Yeah. So let's say we have lambda 1 let's say I just denote this as lambda 1, lambda 2, lambda 3, right? Actually, yeah, no, it's just all the same lambda. So lambda, lambda, lambda. So the arrival rate stays the same. And right, I want to calculate the probability that this number of arrivals from 0 to T1 equal to some N1, and the number of arrivals from T2 to T3. So I can maybe write it as, like, I can write it in a different notation as well, but T2 to T3 as N2. I want to compute this probability, that's it, right? Let me use a notation N of T to denote N of 0 to T. So the number of arrivals from 0 to T. In that case, I can write N of T2 comma T3 as N of T3 minus N of T2, right? Just a notation. So I'm denoting 0 to T as T. So then T2 to T3 will be 0 to T3, number of arrivals from 0 to T3 minus number of arrivals from 0 to T2, right? Because I want the interval in between. So I just change it like this. And so now I want to compute the probability that there are N1 arrivals between 0 to T1 and N2 arrivals between T2 to T3, right? So using this notation, I can kind of rewrite it as P of N of T1 equal to N1 and N of T3 minus N of T2 equal to N2, right? So now, firstly, I know that I can use the property of independent increments. So I know that this quantity and this quantity is independent, right? Because the time intervals 0 to T1 here and T2 to T3 over here are distant. So they don't depend on each other. So I can simply write it as N of T1 equal to N1 times probability N of T3 minus N of T2 equal to N2. I can just, these are independent events, so I can just write it as product of each of these probabilities, right? And so another important property of Poisson distribution is something known as stationary increments. That is, all I need to worry about is the difference T3 minus T2. This difference is what will determine the number of arrivals. So does that make sense? So N of T3 minus N of T2 will be equivalent to N of T3 minus T2, let's say, N of T3 minus T2. Because I only need to worry about the difference. That is, so I don't need to worry about the starting point. So if I draw a time interval, so let's say these are the values, right? T2, T3. Sorry, let's draw it properly. T3. So long as the length of the interval is the same, it doesn't matter where on the time axis I'm lying. So long as this interval is T3 minus T2, which is the same in both of these intervals, it doesn't matter where on the time axis I'm lying, it's always stationary. It always depends on the difference in the time interval. So this difference in time value is what determines the number of arrivals. So I can write it as N of T3 minus T2. Is that clear? So it will be equivalent to number of arrivals from 0 to T3 minus T2, right? So if I make this change, so I'll just have to compute probability N of T1 equal to N1. And we know that this is the distribution, right? Poisson distribution, e to the power minus lambda t to the power n by n factorial. And we need the probability that this is equal to N1. So it will be something like e to the power minus lambda T1 lambda t1 whole to the power n1 divided by n1 factorial, right, times e to the power minus lambda t3 minus t2, lambda times t3 minus t2 whole to the power n2 divided by n2 factorial. So this is how we'll compute these kind of probabilities. And that's a key trick really. Like you have to understand these two properties of independent increments and stationary increments. Is this clear? I can go over this again because these two properties are really important for a Poisson distribution. Like if you understand this, you can solve any problem of this type. Any questions? I'll wait for a minute. Okay. Okay, so I assume there are no more questions. And yeah, so and this can be extended. This is not just for two intervals. I could have easily framed it as this question as n of 0 to t1, t1 to t2, t2 to t3. Like this is equal to n1, this is equal to n2, this is equal to n3. This holds for as many independent intervals as you take. It will just be independent. So you will just have to take product of each of these individual chunks of time, right? Okay. Again, any questions? Then let's do another quick problem. So let's say you have a classroom, let's say in a school. You have a classroom where you have a class that is being commonly held for two sections, let's say. So from one section, you have students coming in at a rate lambda 1. From another section, you have students coming in at a rate lambda 2. And so you want to figure out the probability that the first student, like your queue is empty, you want to figure out the probability that the first student arrives from section 1, let's say. You want to figure out the probability that the first student arrives from section 1. How will you do that? Right. So here we need the property of exponential distribution, right? So again, this is an arrival process with a Poisson rate. So the time taken between the inter-arrival time between two arrivals, or the time taken for the first arrival in this case, for section 1 will be distributed as exponential lambda 1, right? And the time taken for students from section 2 will be exponential for the first student from section 2 to arrive will be again distributed as exponential of with a parameter lambda 2, right? Exponential distribution, as we can recall, exponential distribution is nothing but lambda e to the power minus lambda t. Yeah, so this is like f of t t for t greater than 0, right? This is the exponential distribution. So I need the probability that t1 is less than t2. That the first student that the first student actually arrives from section 1, which means the time of arrival of the first arrival process is quicker. Does this make sense, this logical reasoning? So I want the first student to be from section 1 and I want to find the probability. So this is the case. So again, this is a bit of probability jugglery. So let's say if I fix a given value of T2, let's say T2 equal to some fixed value T2, right? So then probability that T1 will be less than a particular value of T2 will be nothing but this. I have to integrate this PDF, right? Lambda e to the power minus, sorry, lambda 1, because T1 is exponential lambda 1, e to the power minus lambda 1 tt. I have to integrate this over 0 to T2. So this is for a fixed value of T2. So this is, initially I'm conditioning over a fixed value of T2, and then I'll take an expectation on top of that, right? That is how we do it in standard probability. So like, let me just make it clear. This is T1 dt1. You're integrating from 0 to T2 for a given value of T2. And now T2 itself has a probability distribution, right? So you will write it as T1 equal to 0 to T2. And then T2 itself can have any value from 0 to infinity. So this will be, again, lambda 2 e to the power minus lambda 2 T2 dt2. Does this make sense? Right? I could have written it more rigorously, but the intuitive idea is you will first, so this is kind of, remember that there are two random variables here, T1 and T2. So you will have to, when you compute the probability, you will have to take like the integrate over the PDF of two random variables. And so you cannot, so this is a double integration. And so first you'll have to fix one of these variables, which is you fix this, let's say T2 equal to T2, which constrains T1 to be only from 0 to T2. And then you multiply it with the PDF of T2 and then integrate. Does that make sense? Okay. So, okay, now it's this calculation. Lambda 1, lambda 2, these are constants. And then e to the power minus lambda 1, T1, dt1 integrated over 0 to T2. So we can kind of quickly evaluate this. That will be 1 by lambda 1. I think it will be minus, yeah, 1 minus e to the power minus lambda 1 T2 times lambda 2 e to the power minus lambda 2 T2 dt2. Sorry, lambda 2 has been, I've already taken multiplied lambda 2 outside. It will be e to the power minus lambda 2 T2 dt2, right? And so lambda 1 cancels out. And so I have lambda 2 times can somebody help me with this? Lambda 2 times T2 equal to 0 to infinity e to the power minus lambda 2 T2. So this will be nothing but 1 upon lambda 2, right? Minus, so lambda 1 cancels out, minus 1 upon lambda 2 minus, so this will be e to the power minus lambda 1 plus lambda 2 T2, right? If I multiply these things. So this will be 1 by lambda 1 plus lambda 2, right? So then if you take LCM, we will be left with, I think, lambda 1 by lambda 1 plus lambda 2. This should be the answer. I'll not spend more time on this computation, but you can do it and check. And it kind of makes intuitive sense because higher the value of lambda 1, that is the higher the arrival rate, more is the possibility that the first arrival is from the first section of the class. Does this make sense? Like theoretically, if you take it as lambda 1 approaching infinity, this goes to 1. Right? So these kind of computations should be easy to do. Is this okay?
I have one doubt.
Yeah.
How are you making sure that T2 will be smaller for this probability integration? You have fixed the limit T1 from 0 to T2.
Yeah, no, we need T1 to be smaller, right? We want the
yes.
we want the first section. So okay, so is your question that how I'm ensuring T1 will be smaller? So this is from the integration limits itself, right? See, T1 will always vary from 0 to T2, no matter what the value of T2 is. Does that make sense? Because whatever the value of T2, I can only vary T1 from 0 to T2. That is my constraint. So even if T2 is 0, then T1 can only take the value 0, like in a limiting sense. So yeah. It depends on, like, you can also view it in another way. You can fix T1 and then you can, like, this will be equivalent to the integration. Like if you fix, just remember that whatever variable you are fixing has to be integrated out. Like if you are fixing T2, then T1 has to be integrated out first so that you obtain the expression in terms of T2 and then integrate out T2 later. This is equivalent to, let's say if I want to fix T1, right? Initially, so T1 equal to T1, I can solve it this way. So then you will have to integrate T2 equal to T1 to infinity. So you want T2 to be always greater than T1, then dt2, and then you multiply the PDF of. So T1 can be 0 to infinity. So this will ensure that T2 is always greater than T1. These two integrals are actually the same. You'll get the same answer. Both of these approaches are valid, whatever. But yeah, so this, you just have to ensure that you are doing the joint integration properly. Okay. You are, more formally speaking, this, like if I have to do it mathematically, probability T1 less than T2 is equal to nothing but kind of probability. Like I can write it as some kind of expectation of the identity function that T1 less than T2. And then I can do a conditional expectation. So expectation of identity function T1 less than T2. And then I'm taking this, here I'm taking expectation over both T1 and T2. And now I'll take expectation over just, so I'll do an iterated expectation. I'll first take expectation over T1 of the identity function that T1 less than a particular value T2, less than T2. And then I'll take an expectation over T2. So this is exactly what I did mathematically speaking. I first, like if you write down the expectation using PDFs, what I did intuitively, this is exactly, like in a rigorous mathematical way, this is exactly what I did. I broke down the combined expectation into kind of an iterated expectation. That's somewhat, does that make sense? Okay. Okay, so that's fine. Let's cover another important, very important property of the Poisson process. So let's say you are given two Poisson processes, right? And in fact, let's take a proper queuing theory example. You have something like this. You have something similar to the previous example. Actually, you have a class 2, or you have some assembly line in the factory, and you have two workflows coming in, one at rate lambda 1, another at rate lambda 2. So what is, you want to find out the combined rate of arrival lambda, right? This is what you want to calculate. Now you know that lambda 1 and lambda 2, these are both behaving as Poisson processes. So the first question really is, will the sum total, so let's say you have n1, like you have two processes, right? You have x1 varying as Poisson lambda 1, x2, which is number of arrivals from the second workflow, arriving as Poisson lambda 2. What you really want to find is x equal to x1 plus x2. Right? This, you want to characterize this sum total of both of the processes. Now, right, this is what you want to do, right? So x1 is such that, x2 is such that, yeah. So question 1, what is the distribution of x? So like, does x behave as Poisson? Does x behave as Gaussian? Does x behave as, I don't know, binomial, whatever? So any answers or any guesses? And these are independent processes, of course. These are independent workflows, no dependence among them. So, like I should mention it, x1, x2 are independent.
Poisson?
Yeah, it is Poisson. It is indeed Poisson. And so what will be the value of? So this is Poisson. And second question is, can you compute the value of lambda?
Right. It's sum of individual lambdas, lambda 1 plus lambda 2.
Yes, this is also correct. This is also correct. But we need to prove these, right? We cannot just assert these, that this will be the case. So yeah, this needs to be proved, but this is an important property of Poisson processes, that the sum and difference and any linear combination really will be, actually sum and difference will be Poisson, right? Actually sum will be Poisson, yeah. Cannot talk about the difference. So yeah, this can be proved. 1 second.
We can use moment generating function.
Yes, you are right. So moment generating function, this is the way to prove it. And but I mean, you can also do it simply. Honestly, like you don't need MDF, but yeah. Okay, so let's try MDF. M of, so moment generating function for a Poisson process is given as e to the power lambda e to the power t minus 1. Actually, yeah. E to the power lambda e to the power t minus 1. And yeah, so let's say if you have sum of two random variables which are Poisson. So what is the formula for a moment generating function? It is expectation of e to the power tx, right? So here that will be expectation of e to the power t x1 plus x2. And we know x1 and x2 are independent, so we can just take product of expectations. E to the power dx2. And so let's just, and we know x1 and x2 are themselves Poisson. So we can just take, accordingly, we can take these as e to the power tx1 will be e to the power lambda 1, e to the power t minus 1. And this will be e to the power lambda 2, e to the power t minus 1. And so this will come out to be e to the power lambda 1 plus lambda 2, e to the power t minus 1. So you're right, the best way to characterize any random variable is just to use the moment generating function. So clearly this is of the form of a moment generating function of a Poisson distribution with the rate parameter as lambda equal to lambda 1 plus lambda 2. Therefore, this is Poisson. And yeah, Poisson and with a mean rate equal to lambda 1 plus lambda 2. Okay. Yeah, that is that. And similarly, you can solve other. The key thing here is actually the moment generating function. If you know this, you can solve various problems with some difference, any linear combination of Poisson distributions. And yeah, you just need to compute these kind of values. Yeah. Okay. Right. So this is like this is about Poisson distributions in general. And any other questions that you might have before I move on to continuous time Markov question?
So can you please clarify that order statistics of arrival time is like uniformly distributed, something like that? There was a part in that lecture.
Can you
I guess
mention which
lecture 10, I
orders?
believe.
Order statistics is uniformly distributed. I haven't gone through the lectures in exact sense. So I think what you mean is like,
I mean, I'm not
yeah,
able to understand the connection between uniform distribution, which professor was explaining, with the
okay,
Poisson process. I mean, he said something like that. Let me check my notes that given that n event times S1, S2, Sn, the distribution will correspond to an independent uniformly random variable. Not sure.
yeah, okay. So that is almost exactly what I was discussing here, right? So if you this kind of notion of independent increments, right? So yeah, the time, no matter where you are, the time interval between two arrivals is always distributed as exponential lambda 1 or lambda. That is the exponential distribution. So order statistics of arrivals, by that if you mean like first arrival, second arrival, third arrival. So the time interval between these arrivals has the same distribution, which is exponential with the parameter lambda. That doesn't mean that the time intervals will be equal. But all it means is that these time intervals, let's say you denote it as T2, like T2 minus T1 and T3 minus T2. Both of these will have the same distribution, which is exponential of lambda. So that's all. I think That's all I can kind of conclude, because we cannot conclude anything further because it's a random process. And as I said, like if you have to compute that this time is less than this time, then you have to go through that integration route and like compute the values. But yeah, so that's all I can conclude, that the time interval between first and second, second and third, third and fourth will all be distributed as exponential of lambda. Does that make sense? I think this is what he might have meant.
Yeah, I mean, kind of, but I was looking at the joint distribution of arrival times.
Okay.
But anyways, yeah, maybe I'll look more somewhere.
Yeah. So then, like, if you have to do a joint distribution, then it will just break, let's say T2 minus T1 equal to some T1, and then T3 minus T2 some T2. Then this will just break into product of,
Okay.
because these are independent increments, as I was mentioning. The joint distribution is the same as this kind of product of individual distribution, because these quantities are not dependent on each other. It's just complete. That's a property that it will be fully independent of, like this, so long as the time intervals are disjoint. So because that's how this is designed. Like you have 0, T1, first arrival, second arrival, and the third arrival. So long as the time intervals you are considering are disjoint, they will always be independent. They have to be. That is how these kind of matrices are like. That is how the Poisson process is defined, and that is why it is kind of used as a very simple model for Qs. Okay. Here we are. So now, if I move on to the second part, which actually leads on the first part a lot, which is continuous time Markov chains, right? So here you have various states, and so let's say your state space is the state space is 1, 2 till n, and the theory of continuous time Markov chain is that the amount of time you spend at any state, T1, T2, or Tn, is exponentially distributed, right? With some parameter. I don't know. You can do any parameter really, but but the time spent, the sojourn time, as they call it, the time spent in a particular state is distributed exponentially. And then once that time is over, it will jump to some other state, right? And so you have two matrices that characterize that really characterize a continuous time Markov chain. The first matrix is the transition probability matrix, right? So the probability at any time that this one, right? The matrix that we already know from discrete time Markov chain theory is Pij. Is probability that Pij. So you can actually, for continuous time Markov chain, we can write the probability as Pij of t, which is probability that the state at time t xt equal to j given x0 equal to I, right? So this is the probability that that is Pi equal to P. Right? And so the way a continuous time Markov chain is factorized is this probability that there's another matrix Q, the generator matrix. This is the transition probability matrix, and Q, which is the generator matrix. My bad. So this is pertaining to the continuous time Markov chain, but every continuous time Markov chain has a corresponding discrete time Markov chain where we have a transition probability matrix denoted as small pij. So this is probability that the next state will be, so x n plus 1 will be j given xn equal to I, right? That is the probability that you will go from state I to state j in the next transition. So that is how discrete time Markov chains are written. And for continuous time Markov chains, you have a generator matrix Q. So it is a generator matrix Q. So this is what characterizes. So Q is written as lambda I minus lambda I if j is equal to I. So that is kind of analogous to the rate at which you will so you are in a state I. So this is kind of minus lambda I, the rate of a self transition into the same state. Kind of, because it's a little complicated. And then into different states, the rate will be lambda I times Pij, right? For all j not equal to I. So the rate of arrival times the transition probability into the next state. So this will be lambda I times Pij for j not equal to I, right? And so if you are given any random matrix, and so the property here is usually that the summation of Pij, j not equal to I, is equal to 1 usually, because this is a continuous time Markov chain. And so we usually don't keep absorbing states in continuous time Markov chain. You will always be moving. And so you will have this property that the summation of Pij, j not equal to I is equal to 1. And hence, so this Q generator matrix, for every row, for the ith row, let's say, if you sum over all Qi's, ij's for any given I, so if you sum over all the j's, then you will get one value corresponding to j equal to I, which is minus lambda I, plus lambda I times a summation over Pij for j not equal to I, and this quantity, and this is equal to 1, right? So this is equal to 1, so this is equal to 1, right? So this will be minus lambda I plus lambda I, this will give you 0. So this is how you will identify a matrix as a generated matrix or a valid generated matrix, is that all rows sum to 0. So this is one important property. And actually the second and the even more obvious property is that diagonal elements are less or equal to 0, because these are of the form minus lambda. So arrival rates lambda i's have to be greater or equal to 0. So the diagonal elements, which are the Qi's, have to be less or equal to 0, right? So let's say I give you a very random matrix, something like I don't know, Okay, let's say 0, 0, 0, minus 5, 5, 0, and 1, 1, minus 2. Is this a generated matrix? My question is,
No,
why?
the second diagonal element is not negative, right?
Yes, you're right. Yeah, so this is no. My bad. Yeah, this is no because this element is positive. But how about I change it to, let's say I fix that. Does the answer change now?
Yes.
So this is yes, diagonal matrix. This is actually a little. This is actually still no, because like you cannot have you cannot have an all zero like generated matrix. So actually the diagonal elements have to be less or equal to 0, because like this is not a proper value generated matrix in a way, because this entire row is 0. So which means that there is no transition to itself, neither is there any transition to other states. So this will become a weird kind of a sync state, and this doesn't stabilize the matrix. So these kind of matrices are actually not allowed. So I either like here actually what happens is, if I sum over the first row, the entire first row, 1j, it is equal to 0. Right? 1 second, 1 second. Yeah, so it actually satisfies because I need the rows to be positive. Yeah. Yeah, so actually this works. So now it actually changes, because all I need is, and that's the sum has to be always 0, and diagonal elements, even if it's 0, it's fine. So then it's just that this is not very common, but it does change to yes. Yeah, and let's take another example, which is if I just modify it to something like 2, 4 minus 2. How does the answer change now? Yeah, it does become no now, because this row sums up to plus 4, so it's not equal to 0. So yeah, so that is how you will kind of check if a matrix is a generated matrix or not, right? Okay. And let's do another quick problem. And this type of problem actually requires a little bit of revision of solving differential equations. So that we should try and revise it a little bit. So let's say for a continuous time Markov chain, we have some kind of transition matrices, like a general transition matrix. So something like let's say -1, 1, minus, sorry, not 2 minus 2. This is valid, right? Diagonal elements are negative and the rows sum to 1. And so we have something known as the Kolmogorov equations, right? So there is this equation that determines, so the rate of change of the rate of transition from state I to state J will be nothing but the summation of the probability that we have moved from some state I to state K in time T times the rapid, like the rate of transition, like this from the Q, this comes from the generator matrix Q. And so if I sum it over all K, so this gives me the weighted sum of the probabilities of all of the transitions from different states, right? So this is, I think, the forward. This is a backward form, I think. Yeah, back. It's either backward or forward. This is probably backward. But anyway, this is the basic form of the equation. So I want to figure out and solving these differential equations, we can actually get all of these values Pij of t. That what is the probability of transition, what is the probability that at time t, xt will be equal to j given x naught is I. So we just have to solve some differential equations, right? So I want to find in this case the probability that of self transition, like P11 of t and P22 of t, right? So again, I'll just write down the Kolmogorov equations. P prime, like 11 of t equal to, so P, let's put k equal to 1 first. So P11 of t times q. So here I equal to 1. This is I, this is j. I equal to 1, j equal to 1. So I have P prime P11 of t times Q11 plus P12 of t Q21, right? And so from the Q matrix, Q11 is -1. And Q21 is 2 plus 2, right? Plus 2. Okay. And similarly, and I can write similarly P prime 22 of t equal to like again 2 1. So k, so now I equal to j equal to 2. Let's put k equal to 1 first. So it will be P21 of t times Q22. So Q22 is -2, so it's -2, and plus P22 of t. So k will be equal to 2 now. So P22 of t times again Q is 2 and 2. So Q22. So Q22 is -2, I think, if I'm not wrong. So P22 of t yeah, Q22. So this is -2, and this will actually be P21 of t Q12. So 1 2 is +1. Okay. So yeah, so this is 2, this is 2, this is 2, this is 2, and this k will go from 1 and 2. So I have to solve this system of differential equations here, and so let's see. So we have two initial conditions, right? P11 of 0 equal to 1 and P22 of 0 equal to 1. Why is this? Because in 0 time, so if x naught is equal to I, then again, if t is equal to 0, then x0 also has to be equal to I. There will be no transition in 0 time. So the probability of self transition is always equal to 1. So we have this for any differential equation. If you remember, we get a general solution and a particular solution. So for the particular solution, we need these initial conditions. Right. And we should also remember that like this is again common sense, right? The sum of all transitions at any time t. So it doesn't matter like what is the state I and the state t. The sum over all j has to be equal to 1, right? Because again, this is common sense. Probability that xt is equal to j given x not equal to I. So if we sum it over all j's, then we should cover every possibility, right? It will either go to itself or it will go to some other state in the state space. It cannot go anywhere beyond that. So this we have to keep in mind. And the reason we are writing this is we want to get rid of these guys. We don't want to deal with the cross terms. So we'll just do a little bit of mathematics. We'll add P11 of t on both sides here, right? So what we will have, so this is equation 1, this is equation 2. So to 1, what we will do is we will add P11 of t on both sides. So we'll have, sorry, we'll have 2 times P11 of t on both sides. So this will be, and the reason I'm doing it is it will be very evident. And so 2 times P11 of t minus P11 of t will give me P11 of t, right? And sorry, no, I should write it properly. So let me leave this term as it is with minus P11 of t. And this is equal to 1. I know this, right? Because it has to either go to 1 or 2. It cannot go anywhere else. So I eliminate this cross term. And so this equation becomes P11 prime of t plus 3 times P11 of t. Somehow magically it comes out to be 0, right? And sorry, it doesn't come out to be 0, right? This is equal to 1, so this comes up to be 2. 2 times 1 is 2. And then similarly in the second equation, we'll again try to get rid of the cross term. So we add P22 of t on both sides, right? So that P21 of t and P22 of t add up. So we'll have P prime 22 of t plus P22 of t equal to this P21 of t plus P22 of t minus 2 times P22 of t. So these two guys will again add up to 1. And so we'll have P prime 22 of t plus 3 times P22 of t is equal to 1. So I have these equations 3 and 4. Does it make sense up to this point? So these are kind of the rate at the this is how the behavior defined Kolmogorov equation. And so we have to solve now to obtain solutions for P11 of. So we have again a system of equations. Actually, these are two disjoint system of equations. There is no coupling. So we have to solve 3 to get P11 of t. So this will give us P11 of t. And this will give us P22 of t, which is what we need. Okay. So Both of these equations are of the form. Both of these equations are of the form y prime plus p of x times y equal to q of x, right? So this is the form linear differential equation. And so we need to multiply it with an integrating factor, which is e to the power integral p of x dx. And so we need to multiply both sides with the integrating factor and solve. So how this works out is like e to the power integral p of x dx dy dx plus y times y times px into e to the power integral px dx equal to q of x e to the power integral px dx. So I'm multiplying this integrating factor on both sides. And so this quantity, if you recognize this, is nothing but if you use product rule over d dx of y times e to the power integral px dx, this is exactly what you get. You first take e to the power integral px dx out and you do d dx over y, plus you take y out and then you do d dx over e to the power integral px dx. This is what you get, right? Does this make sense? And then you can solve it, so on and so forth. So then the solution to this will be something like y e to the power integral px dx equal to integral of qx e to the power integral px dx, again integrating over dx, right? Plus, yeah, so whatever this integration gives. Something like that. So I just kind of quickly revised it because you will need it to solve these kind of problems. So let's solve the first one. P prime 1 of t plus 3p 1 of t equal to 2. And yeah, so you have here px as 3. So you will just multiply with e to the power 3t, right? And e to the power 3t p11 prime of t plus 3 to the power 3t p11 of t equal to 2 e to the power 3t. Because again, e to the power integral px dx is integral 3 dt, which is equal to e to the power 3t. This is what goes in here. And here, and here, and here. I'm multiplying on both sides. And now if you just see that this is nothing but the derivative of p11 of t e to the power 3t is equal to 2 e to the power 3t. And so if you get rid of the derivative, it will be nothing but 2 into e to the power 3t dt. So that is nothing but 2 by 3 e to the power 3t plus some constant, right? And then, so if you actually see p11 of t will be 2 by 3 plus some constant and e to the power minus 3t, right? Now this is a general solution. For particular solution, you need to substitute the property that p11 of 0 is equal to 1. If you put t equal to 0, then you will get c equal to 1 minus 2 by 3. So it's 1 minus 2 by 3, that is 1 by 3. And so So then you get your final form of P11 of T equal to 2 by 3 plus 1 by 3 e to the power minus 50, something like that. Yeah. Similarly, you can also solve for P22 of T. It's a similar differential equation which you need to solve. Is anything that's not clear here? Wanted to take some time. Let me go over any of the steps again. You will get these labels, but like yeah, like anything I can answer live, that would be best. Okay. If there are no more questions, I'll jump into another topic. Actually, continuing on this, so P22 of T, I believe, will come to be something like, has anybody tried to calculate using the other equation? I think it should be just, we should replace 2 with 1 wherever and the other way. So it should be something like 1/3 plus 2/3 e to the power minus 3t. And so my question is, if we take here the limit as t approaching infinity, will we get a steady state like transition probability? Do these values converge to some finite value? So let's say if I have to write as P11 and P12, P22, if I drop the infinity and like if I just take t approaching to infinity, does the limit exist in these cases? It does, right? Because t approaching infinity, these two terms go to 0. So this is 2/3 and this is 1/3. So this is kind of the notion of having a limiting distribution. So like this is kind of hand waving, but the formal definition is that So let's say you have a state space, right? In a Markov chain, you have some set of values. Your variable is I, and this I belongs to some set of values S. And you want to find the values Pi's, right? The probability that at kind of at infinity, like Pi, so like essentially Pi is nothing but probability that at any time t is nothing but probability that at any time t xi, xt is equal to I, right? Something like that. The probability that at any time t is equal to I, and you want to check that if t approaches infinity, does this probability approach a certain stationary value pi, right? So for this to happen, there are two conditions. So we need two conditions to be fulfilled. First is the this vector p, because for all I belong to S, if I kind of just stack them up, I'll get a vector p, right? So this will be p1 till, let's say, pn. So this vector p has to be kind of the left null vector, I think, of the transition matrix Q, which is usually the characteristic of any continuous time Markov cell. So this has to be equal to the zero vector. So in other words, summation over all j pi times qij is equal to 0 for all I, right? And the second condition is that the sum of like for all I, to be more specific, for all I belonging to the support set. And then if I take sum over all I for all the PIs, like we need to get this, right? We need to have that at the steady state at t approaching infinity, we should have the probability of existence of each of these states has to sum up to 1, right? So these two are very key properties, and we need both of these to be satisfied in order for a CTMC. So we can say that the continuous time Markov chain has a stationary distribution. That is, if we look at this Markov chain at time t equal to infinity, we have somewhat of an idea as to what is the probability, as to what state the system can exist in, at least with some probabilities that we can kind of get an idea. It's not completely, it does converge to some stationary distribution. Does that make sense? Okay. And from here, you have the something known as the global balance equations. That rate of inflow is same as rate of outflow, right? So at any state I, like you are at a state I, you can either go to, like there can be some outflow to another state J, and there can also be some inflow back to the state I. And so for for like stationarity, for steady state to exist, we need inflows and outflows to be balanced. So there shouldn't be any lingering flows. So then, like, you can mathematically show it as the probability of, so the inflow has to be equal to outflow. So the inflow will be, right? This is for all j not equal to I. Because you're coming from other states back to your own state. This has to be equal to the outflow. That is, you're going from your state to other states for all j not equal to I. You could prove this, but this property has to hold. So probability that you are in some other state j and coming into the state I, if you take the sum probability of that, it has to be the same as if you take the probability of outflow, which is from state I, you are going to some other state. There shouldn't be any transience in anything. It should all kind of be taken care of by this global balance equation. This has to be true, right? So with this, we come to the most important idea, which we will need actually for queuing theory, and that is of birth-death process. Especially for queues, this is very important. Before I move to birth-death process, I want to ask if there are any questions regarding this. So actually, like this global balance equation, which is very intuitive to understand, you can derive it from here, from these properties. You can derive it from here. So that is why these properties are important, because otherwise the global balance equation will not hold, and we will not have any way to characterize the steady state behavior of a continuous state Markov set. Yeah. Okay. Okay, so let's draw then about that process. So so let's say the state of the system is X, which is, we can actually write it as a Q. So you have a Q here, and you want to count the number of elements in the buffer. And so you have these, let's say these people in a queue, they are being served at a service rate mu, and people arrive at a rate lambda. So, and then you are kind of observing the queue length here, which is X. So very clearly, you can only have at any time instant, you can only have two things happening, right? You can either go from state I to I plus 1, which is when you have a person moving into the queue, or you go from I to I minus 1, which is when a person is served and the checkout counter, let's say, and moves out of the queue. So these transitions of coming into the queue, because they, like that is how your queue length increases. These are at the rate lambda, and then the rate at which customers move out of the queue is mu, right? This is a very simple initial queuing model. This is an example of a birth death process because, like, as the name says, there is a birth and a death, birth and a death. There are no transitions in this process. Any transition of this kind cannot exist. So you'll only have a transition between neighboring states, 0 and 1, 1 and 2, 2 and 3, etc. You won't have transitions between non-neighboring states. So that is how these processes are defined. Right. So now you want to calculate the quantity that, like at steady state, at time t equal to infinity, you want to calculate all of these probabilities, P0, P1, P2, till infinity. The probability that the number of elements in the queue will be 0 at t equal to infinity, 1 at t equal to infinity, and so on and so forth. So at steady state, like at t equal to 0, okay. So one property should hold is that the summation of Pn for n equal to 0 to infinity, this has to be equal to 1. We'll keep this equation aside. That it has to exist in either of the states from 0 to infinity, right? Here we are not assuming any bottleneck on the queue. So we can accommodate as many passengers as they flow in. We don't have any maximum limit. We can solve those kind of complicated cases later. Actually, we will go into those details in the next week, but I'm kind of giving a preview because it's necessary. So this queue is known as the MM1 queue. We had discussed in the previous lectures that the service time is exponential and the arrival time is exponential, and there is one server. So we don't have multiple servers in this one server. It's known as an MM1 queue. Now, how do we solve for this probability? We have to write down the global balance equations. How do we go about that? Let's say at state 0, we have the probability P0. And so the outflow from state 0 is very clearly only from 0 to 1. So let's write the outflow equation first. So P0 times lambda, that's the rate at which it moves out. And then the inflow is nothing but mu times P1, right? That is the only way you can come to state 0, which is from 1. If you have a transition mu, you'll go to state 0. So we firstly have P1 equal to lambda by mu times P0, right? This is the first equation. And then let's see. For the state 1, inflow is from either 0 or 2. Oh, sorry, let's write the outflow first. Outflow is either into 2 or into 0. So both are from 1. So P1 times the outflow, that is lambda plus mu. Sorry. Yes. P1 times the outflow, that is lambda mu, has to be equal to the inflow, which is again from 1 the outflow is to this direction, this inflow is from 0 and 2. So P0 times the lambda plus P2 times mu. So this is another equation that we have. And so you have this value P1 equal to lambda by 2 times P0, lambda by mu times P0. So if you solve it, actually, you will, if you put this in this equation here, then what you will get is P2 equal to, I believe, lambda by mu whole squared, lambda by mu whole squared P0. And similarly, so on and so forth, you will actually get the n equal to lambda by mu whole to the power n be 0. And so now, so if you observe, if we only know the initial states probability P0, we can calculate all of the others. And for that, we have one equation which we have left at the side, that this summation has to be equal to 1. So summation of lambda by mu whole to the power n P0 for all n equal to 0 to infinity has to be equal to 1, which means P0 is nothing but 1 upon summation n equal to 0 to infinity lambda by mu whole to the power n, right? um, is this clear till now? And so if you put P0 here, you will get the answer. But if this is clear, let's think mathematically. This denominator has to converge to a certain value, right? Some finite value. When will that happen? When will we have this denominator term converging to a certain value? So we can have these three situations, right? We can have lambda less than mu, we can have lambda greater than mu, and we can have lambda equal to mu. What will happen in each of these three cases for this term in the denominator? So if arrival rate is less than service rate, arrival rate, let's do the other order, equal to service rate and greater than service rate. What will happen in each of these cases? So this is the sum of a geometric progression series, right? So when will this sum exist? When, like, if you have a GP series,
When mu is greater than lambda.
yeah. So for a GP series summation r to the power n to exist, you need mod r less than 1, right? So that is why you will need lambda by mu less than 1 or lambda greater than mu. So in this case, it will exist. And so then the answer for this summation is 1 by 1 minus r, right? So this will be P0 equal to 1 by 1 minus lambda by mu. So this will become 1 minus lambda by mu. I think I'm right. Yeah. If I'm not wrong, this will be the answer. No, my bad. This summation is actually well known. This is second. This is nothing but e to the power. This is nothing but e to the power lambda by mu, right? Oh no, I think I was right. Yeah. Yeah. Which is 1 by 1 minus lambda by mu. Anyway. So and then if you put P0 into all of these, you will get the values. Right. And so if lambda equal to mu, this summation doesn't converge. It becomes a borderline case actually. It will, right. Yeah. So in these two cases, it will not converge. So this kind of gives us a lesson that Like these are examples of continuous and Markov chains with no stationary distribution. So intuitively speaking, if you have a queue and you have more arrivals in the queue than departures, like on an average sense, your rate of arrival is greater than the rate of departure, then obviously your queue will your queue will never stabilize to a steady state. It will always keep the queue length will always keep increasing. It will always be a buffer bloat kind of a situation. That works terminology, but the queue will always keep increasing. You cannot, unless you have, let's say, some kind of finite limit on the number of people you can serve. If you don't keep any limits, it will just the queue length will keep on increasing without any bound. So that is the significance. So that is when, like mathematically, if you that kind of queue will be modeled as a CTMC with no stationary distribution, no limiting distribution, or steady state. So there are equivalent terms. So stationary is same as limiting, same as steady state, all the same. We can have a continuous time Markov chain which doesn't have I guess stationary distribution. I think that's pretty much all I had to cover. I'll wait on the Zoom call if there are any more doubts till 5 o'clock or any other clarifications you might need. This week actually kind of winds up the mathematical kind of foundations that you need. After this, it will be completely focused on actual modeling of queues and various formulas of performance measure, and so it will be much more engineering like. So yeah, but and calculations mostly. So
Thank you, Samya. I'll drop then.
okay. Mhm. Hello. Who are you? Hi, Sangeet. Do you have any questions in particular? Because I'm mostly done with what I had to cover for this week. I'm just waiting. Yeah, but any questions I can answer. I have 20 minutes now.
No problem, Somi, actually. Can you hear me?
Yes, I can.
Yeah. So anyway, so today I had some, I mean, like, unfortunately, I had some work, so I couldn't able to attend. So I think this will be shared in the, I mean, like YouTube, right?
Yes, I will. I
So,
will. After the meeting concludes, I'll upload it to YouTube, and I'll also be sharing the notes that I made in the class. So yeah, that. Yeah.
okay. So what have we covered from 3 o'clock mainly? This
So
topics.
it's just week 3. So there were two main topics that were covered in week 3, which is firstly Professor covered the Poisson distribution and its properties in lot more detail, and secondly, those properties were used to derive and to introduce continuous time Markov chains, and how and so slowly, like like from studying basics of continuous time Markov chain and Kolmogorov equations that kind of govern the functioning of like the transitions between different states in the continuous time Markov chain. So these are the basic stuff, and from generated metrics you can write down Kolmogorov equations, and then you can predict what will happen. The transitions from one state to another state, and eventually the key idea is that we need for realistic systems, we need to have this property that the continuous time Markov chain has to converge to a certain steady state. That so the key property for continuous time Markov chain is that whatever, it doesn't stay in a state forever, it will be staying in a state for a certain time which is exponentially distributed, and then it will move to another state. And so at t equal to infinity, however, if a continuous time Markov chain has a certain steady state, we should be able to predict these pi values, that is what probability, what is the probability that the system exists in a certain state I, right?
Can I ask? I think this is this the one that is called a finite state distribution? That is, after
Yes,
this many states,
yes.
it becomes steady. The row sum, I mean, the row values becomes steady.
Yes,
Okay.
you can call it. Yeah. So then you achieve a stationary distribution.
Okay.
And so for in the stationary distribution, you will have these global balance equations that will hold. That is the rate of inflow at any state, like the rate of coming into that state from other states, will have to be equal to the rate of outflow. That is the rate that you will move out of the state into the other states. So that those rates have to match, so that there are no transients remaining and everything balances out. So this is global balance equation. And with that, we went into the notion of birth-death processes, which you need actually to solve to model queues. So we did the example of an MM1 queue, where MM1 queue, as you remember from that notation, is that arrivals and
It's Kendall's notation.
Kendall's notation, arrival and service is both exponentially distributed, and you have only one server. So you can predict the probability that there are n elements in the queue using these properties. So firstly, you have this equation that summation, like you need to have the sum of probabilities. One second, let's slow. So this second idea, right, that the sum over all probabilities has to be equal to 1, and you also have to have the global balance equations So if you use both of these, solve for both of these, you can actually derive the MM1Q formulae, that is the probability of having n elements in an MM1Q. And then through simple, I didn't, I kept it simple here. So for this particular example, it's very easy to see that this sum of the GP series here, which you get for P0, this has to converge. This sum has to converge to a finite value for the stationary state to exist, because all other PNs depend on P0. And so for this to converge, for a GP series to converge, sum of a GP series to converge, we need that the common ratio, the lambda by mu has to be less than 1. So we need lambda less than mu. This is so we need the arrival rate to be less than the service rate for stability. So if we don't have that, if we have arrivals and service at par or arrival more than service, we will not have a stationary distribution. This is an example of a continuous time Markov set without any stationary distribution. What will happen in this case is we will have more arrivals in a queue than we can serve. So we'll have more arrivals than we can serve. So eventually, in like at time t equal, like we will, on an average, we'll always have the queue led to be increasing, and so it will never like converge to a steady state. It will spiral out of control. It will be infinity. So that is the idea. Does that make sense?
Okay, yeah, fine actually. So at least, yeah, I got some idea. I know a little bit, but after I think I had to go through some continuous time. I haven't started. I just try to go through it.
Yeah. So this is kind of the key idea. So this, as I was telling to the other students there, this week is very critical also, because this is the last piece of the puzzle you need. Like this is the also foundations or fundamentals. And once you know this, once you know how to handle birth type processes, then the rest of the course is mostly plain calculations. And like, so if you understand this week's concept, the rest of the weeks, it's much easier to cover. It's just that there will be wide varieties of problems that you can solve, but like the basics are like these week 0, 1, 2, and 3. After that, whatever is there is just primarily this different kind of mathematical manipulations and calculations. That's all.
Okay. Okay. Thank you, Sumya. Like, I mean, like, yeah, that's fine. So maybe I replay the recording and then I'll just see.
Yeah. So,
okay. You have anything more to explain? That's it for today's class.
for today, yeah, this is what I had. Yeah, I just want to go week by week. So, like, you can ask any doubts if you want. I will still be on call for 10 more minutes. But yeah, any doubts from previous weeks also is fine. But yeah, otherwise.
Yeah, I don't. If I have any doubts, maybe I'll ask definitely in the next class. Okay.
Okay.
Okay. Okay. And see you next week.
See you next week.